Welcome back, everyone. We're going to finish off our discussion on tensor operations by talking about a couple of matrix-based operations that we won't see too often throughout the course, but it is good to know that they're there for us in PyTorch. Let's head back to that notebook. Okay, here we are back at that original notebook. So right now, if I take a look at A, I have 4, 10, 18. Let's go ahead and reset it to 1, 2, 3. So I'm going to scroll back up here and just copy this line where we had A is equal to 1, 2, 3. And so now if I check A, I have it as the tensor 1, 2, 3, and B is still 4, 5, 6. Now, typically, when you say A times B, when you just do this with PyTorch tensors, what it does is it performs on an element by element operation. So it takes every element at this index on A and then multiplies it by the same index location element at tensor B. So this is not actually true matrix multiplication. In fact, there's two ways of multiplying matrices. One is a dot product, and the other is true two-dimensional multiplication. And keep in mind, if you haven't taken a linear algebra class, you may not be familiar with things like dot products or matrix multiplication. So if you check out our actual notebook, we have a little quick review on that in case you're interested. So we have a little review on dot products in the lecture notebook, as well as a discussion on matrix multiplication and some helpful links for you to check out there. But we're going to quickly just show you the PyTorch syntax for performing those. So we'll go ahead and come back to our notebook here, and we'll first start off by showing you how to perform a dot product. The way to do that is instead of saying A dot multiply by B, since that performs element by element, if you actually want to perform a dot product, you say A dot B, and that will perform a true dot product. And you can check out more information about what a dot product actually is by checking out the link and discussion in the lecture notebook. But we won't really be using dot products that much throughout the course, so don't worry about this too much. We'll review it in case it comes back up later. Then for 2D matrix multiplication, that's only going to be possible if the actual tensor or matrix shapes match up correctly. So in order to do this, the number of columns in the first tensor needs to match the number of rows in the second tensor. So essentially, if we multiply A by B, the number of columns in tensor A needs to match the number of rows in tensor B. So let's go ahead and create a new tensor. We'll say torch tensor, and I'm going to make this two-dimensional. So I'll have 0, 2, 4, and then 1, 3, 5. Go ahead and run that. And so here we have 0, 2, 4, and then 1, 3, 5. It's a 2 by 3. And then what we're going to do for B is we'll say torch.tensor, and then we'll say 6, 7. Actually, what we're going to do is we'll say 6, 7, and this is going to be a 3 by 2. So we'll say 6, 7, and then the next row will be 8, 9, and then the next row will be 10, 11. So we'll go ahead and run that. And we have B here, 6, 7, 8, 9, 10, 11. So again, notice the shape of these. So we have a 2 by 3, and then B shape is 3 by 2. So the number of columns here on A matches the number of rows on B, which means we can perform matrix multiplication. And the way you do this is you call torch dot, and then you're going to say MM, which is matrix multiplication. That's what it stands for. And then you can pass in AB, and it returns back the true two-dimensional matrix multiplication. And the shorthand for this is, instead of an asterisk, you can use the @ symbol. So you can say A at B, and that will also perform matrix multiplication. Although I would suggest, just for reading the code, since @ is used for decorators sometimes in Python code, I would highly recommend you use torch.mm. But keep in mind, if you do see the shorthand, such as A at B, that's performing just normal two-dimensional matrix multiplication. The last two advanced operations I want to discuss is L2, or Euclidean norm. The Euclidean norm, in case you're not familiar with the equation, we do have it for you here in the lecture notebook. So if you scroll down, we're right now on advanced operations. So Euclidean norm, this is the formula right here. Sometimes people actually call this the magnitude of a vector if you just have a singular 1D vector. So you may have heard it that way as well. But what we're going to do here is we're just going to show you how to actually grab the Euclidean norm. And the way we're going to do that is we can say x is equal to, and let's go ahead and define a tensor. We'll say some tensor 2, 3, 4, 5. So note those are floating point numbers. So here's our tensor. What we're going to do is ask for the norm, and that returns back the Euclidean norm. And then what you can also do is grab the number of elements. So often it's useful to actually grab the number of elements inside a PyTorch tensor. So to do that, you can just say num el, and that returns back the number of elements. So in our original tensor x, we had 4 elements, 2, 3, 4, and 5. And if you use length on x, that will also return back the number of elements. And if you check a 2-dimensional array, such as A, so note we have A here. If you were to check the length of A, it actually would only return back the number of rows. So keep in mind, that won't be effective when you're talking about a 2-dimensional matrix. So for that, you would again need to say A dot num el, and that will give you back the total number of elements inside that tensor, which is 6. Okay, so that's it for advanced operations. We really won't see these too often, and if we do see them later on in the course, we'll make sure to do a more thorough review over things like Euclidean norms or matrix multiplication or number of elements. So don't worry too much about having to memorize these. You may see them a little bit in your exercises, but if we do encounter these again, we'll do a thorough review. Thanks, and we'll see you at the next lecture.